Dr. Venkat Krovi is an esteemed researcher and professor at Clemson University, where he holds the position of Michelin Endowed Chair and Professor of Automotive Engineering. He is a renowned expert in the field of robotics, automation, and control systems with a particular focus on their application to the automotive industry. His work has been recognized with numerous awards and honors, including being named a Fellow of the American Society of Mechanical Engineers. At the AI Summit, Professor Krovi discusses the exciting topic of autonomy and automation supercharged by AI. Autonomy and automation supercharged by AI is an important topic because it addresses one of the most significant technological advancements of our time. The integration of artificial intelligence with autonomous and automated systems is already transforming various industries, including transportation, manufacturing, and healthcare. In the automotive industry, the use of AI-powered autonomous and automated system has the potential to revolutionize the way we think about transportation, making it safer, more efficient, and more environmentally friendly. It is also an area of great interest for researchers and policymakers who are exploring ways to optimize and regulate these technologies. As such, understanding the opportunities and challenges associated with AI-powered autonomy and automation is essential for anyone interested in the future of the technology and its impact on society. So let's welcome Dr. Krovi.
Morning, everyone. It's always tough to get things started. So I thought, I was given this dubious distinction of getting this series kicked off. Time will tell. But the title I had intentionally set up as Autonomy and Automation Supercharged by AI, because I wanted to highlight the fact that, autonomy and automation has existed way before AI even came around, right? And it will exist perhaps after AI too. But there are some things that AI can do that allow it to do things much, much better. So in this, as I go through this presentation, I'll talk about deployments that we have in the on-road, the off-road, and the manufacturing shop floor setting. And I'll be mixing some of these examples. But the thing that I'd like you to keep in the back of your heads is that each one of them is a vehicle, right? There's a total life cycle of the vehicle that one would want to consider. So when you start to think about from concept cradle to grave, what are the types of aspects that one would want to look at? So before I get started with the actual AI infusion portion, wanted to give you a sense of what my mind map is for autonomy. Autonomy doesn't exist in a vacuum for me. It's actually a trifecta of autonomy by itself. So you have the sense, think, and act, and to do this in real time. But you also have networked operations. And so you have deployments from a computation and communication perspective that span a variety of scales. And last but not least, and perhaps most important, is the human in the loop. And so if you think of these as three legs of a stool that support this overall deployment, what you're seeing is that it's actually a multi-hierarchical framework. So on the autonomy front, you can deploy autonomy at the component level, subsystem level, system level, and system of systems level. On the human front, you can think of individuals, small groups, crowds. From the networked operations, you talk about cloud, mist, fog, different kind, thin edge client. And so as you start to now apply this in different regimes, so in the automotive sense, the ability to do this at ECU level, connected by a CAN bus, has existed for a long time. But increasingly, we are starting to get into vehicle level automation, where you now have sensors that are exteroceptive, that are looking out of the vehicle, and increasingly connecting to different information sources that are giving you over-the-air updates in the context of, let's say, smart city. Very similar types of things occur when you now think about autonomy at the individual mobile manipulator level, and you start to think about cell level autonomy and then perhaps even connecting to a manufacturing execution system. The one thing that is common to all of these is that complexity has grown, but you have this unique ability to get digital insight into what was traditionally an analog world. So people talk about data as the new gold, sure, but how do you use this data? Is all this excess data even meaningful? Is a question I think that we've opened up a Pandora's box, in my opinion, and maybe there is hope at the bottom of that. So being able to engineer back capacity in such systems, such that the whole is greater than the sum of the parts, is where some of the opportunities now come. So just a shout out to give you a context of where we are deploying a lot of these. This is now work I'm representing for several of my colleagues who themselves give individual talks, where we do things at the small scale, typically the types of things where we teach our students, do mid-scale projects. These are now individual studies, but there are also full-scale vehicles that we work with, and we're happy to talk to you. I think Dr. Jay will talk about his work, and we can talk about this after. So I wanted to give a shout out to one particular project called the OpenCAV project that started about 2018, I'd like to say, where 20 plus faculty around Clemson were all doing different facets of autonomy, and they all needed a vehicle to be able to test. So we are looking at doing things at enterprise scale, and oftentimes it requires enterprise scale architecture and enterprise scale tools and workflows. So one of the things that we worked on was setting up simulation as a service. And so I think since you're all here, you can see the campus being modeled here. But what is crucial is that it's not the one-off simulation, but to set it up in a Kubernetes orchestrated Dockerized simulation so that you can now scale these simulations to different initial conditions to be able to do this at scale, so that you can start to do things like variability analysis. You have the ability to now also use simulation as a way to build out your algorithm, test it, do an initial refinement, virtual prototype. But then ultimately, it's the sim to real gap that you're looking to address so that you can actually test this in the prototype vehicle. So in that sort of broader context, all that was background, I wanted to hit upon some of the challenges that come and why AI has proven to be so useful to us. So what you have here is an explosion of complexity. If you think things that you could do within the car was contained within the car, now as you start to increase the scope to all the sensors around the car and then to the smart city, your volume of interactions has grown. And so how does, you can do these one-off deployments, but then how do you do systematic verification and validation? And how do you now take into account a lot of these new capabilities? So the auto industry traditionally has built off the ISO 26262 model, which has proven to be very useful in being able to deploy. But I wanted to offer some additional pieces of data, and we can have a conversation about this after. One piece of data is that, even back in 2009, I'm quoting an article from 2009 in IEEE Spectrum, a modern day car at that day, in those days, had 100 million lines of code. And so what you have there is a software-defined vehicle, if you wish, right? And so that's enough complexity all by itself. But the fact is also that the auto industry has built upon many decades worth of legacy systems, right? And so the dependencies that you have between a system that was perhaps developed, refined, and deployed back in the 80s to one of these newfangled AI-based systems that's just come around, there needs to be a systematic approach to handle that. I'm not saying that we have the systematic approach. I'm just identifying the problems. So, it's no surprise that, the complexity and the competence that one requires in order to be able to verify this, there's a gap, and that gap is growing and will continue to grow unless we do something about it. So, in that sense, right? So, what are a few things that we believe, would be needed? And in particular, how do we, we are a university. So, our product at its core are our students. And so how do we train our students in some of these new methodologies so that they then become capable? So first and foremost, right, I think is an acknowledgement of the fact that what we are dealing with are big data problems. I mean, we have to have the tools and the experience and the capabilities to handle big data. In all, it used to be the 4 V's of big data. Now it's 10 V's, what have you. The second thing is, deep learning came out of left field and has changed how we do things. So very often I ask this question, back in 2016, somebody graduates, what would they know about deep learning? What are the chances, right? And, now they're in a full-time position, they have a day job, and they're learning deep learning on the side when actually deep learning as a concept requires lots of experience, practice. The third piece is that we're not talking about, especially in the automotive and in terms of automation, we're not talking about deep learning and machine learning being done on a server somewhere in the cloud. We're talking about real-time performance, oftentimes at 100 hertz or higher. And last but not least is this idea of CI/CD, so continuous integration, continuous development, that you create. Robotics has always sort of built upon this idea that you build an end-to-end product and then you continuously refine it. And so if you were to imagine these as being sort of enabling technologies, paradigms, frameworks, how do we get our students familiar enough with this suite of tools that they can become potent as they leave? So to put all this in context, right, I just thought, let me pick a few of these simple examples that, closed loop control of some vehicle operation, let's say automatic emergency braking, or lane keeping, or what have you. So it's clear that, you've had first principles models for this for a long time. But now the ability to replace some of these first principles models with AI techniques is where the opportunity is coming. So what are the possible places you could do it? Well, in terms of characterizing the vehicle dynamics, all of us have done Lagrangian, Newton-Euler formulations, etc. But now, can you do an AI enabled data-driven system identification of the vehicle while it's running? You've got different types of controllers possible that previously, were not in the realm of possibility. You can start to put in different road conditions. I think people get the idea. So I wanted to quickly then run through some of the types of things that we are doing in the course of various projects. The first one is actually, I wanted to give a shout out to Dr. Luo. This is a view translation project where, many of these ADAS systems depend upon that front camera in order to be able to function. But what happens if that front camera is busted? And you now use an AI-based system to now replace that. Or if you said, I wanted to have semantic segmentation that then allows you to now build out these different maps. On the other hand, we've also got people now working on different types of imitation learning, deep reinforcement learning methods that very often they end up trying out on limited examples, small scale examples. But I think the one thing that I keep repeating is that it's not the size of the vehicle that matters anymore. It's the size of your code base and your ability to handle that code base. And so if people are interested, I'd be happy to talk a little bit more about some of these as we move along. 2 more slides. The last thing I wanted to highlight is that it's not just in terms of the algorithms that go onto the vehicle itself in some of the different subsystems, but there's an opportunity now to refine the entire workflow and to use AI and AI-based automation to enhance how you do requirements analysis, how do you refine the design, and how do you implement and test these. And so in this context, we have an active project that is just started under the Viper.js, where we're using cloud-based simulation, scalable simulation, together with the vehicle-in-the-loop testing. So there's a AVL driving cube that we're installing downstairs that allows us to create essentially a virtual and a physical test stand that then allows us to beat that system to exercise all of its capability. The question is, do you want to do a full factor Monte Carlo analysis, or should there be intelligent methods like, design of experiments, sequential sampling, other methods that can help to minimize that? So again, I'm just, in the interest of time, right, I'm just showing this. And this is not restricted solely to the automotive on-road domain. You can actually do this now in different domains. And shown here is taking advantage of, the Isaac Gym environment, Isaac Sim, Isaac Gym environment to be able to do large-scale training in parallel, and then ultimately deploy this in different systems. So thank you.